Hey GED students, it's GED question of the daytime. And again, we're reducing fractions. And reducing fractions is just one of those concepts that GED students panic about. But there's a lot of easy tools that you can use to help you see when two numbers have a common factor. All it means to reduce fractions is to divide out any common factors. So the most important thing, so I'm going to just circle the word reduce. What does it mean? It means to divide out any common factors. A reduced fraction is one where the only factor they have in common, the only thing that can divide both numbers, is 1. So the trick here, though, is not doing the actual reducing. The trick here is finding the common factors, and that's what students struggle with. So the first tool in the last video we did, check it out if you haven't, is to use your divisibility tricks. The more divisibility tricks you know, the easier you will find fractions. Those divisibility tricks are also known as divisibility rules or tests. They're just basic patterns in numbers that people notice. And if you can notice these patterns like I notice these patterns, you won't find fractions hard to reduce at all. But what should you do when your divisibility tricks fail you? Like I'm looking at these two numbers, and I'm not going to be able to find a factor of 2 because they're not both even. I'm not going to be able to find a factor of 5 because they don't end in 5 or 0. It looks like if I look at this top number, 42, a sum of digits will work for 42. 4 plus 2 equals 6. That's on the 3 times tables. So I could find a 3. Again, that's called a sum of digits trick. But I would fail with 77. If I added 7 and 7, I'd get 14. There's no 3 in there. And divisibility trick after divisibility trick fail me. What should I do in that case? Should I just assume the fraction is reduced and move on? Turns out we have another tool we can use. So if you're struggling to find a common factor, my advice to you is to use a factor tree. A factor tree is a tool that we have in math that allows you to see every prime factor that a number is composed of. I kind of like liken it to looking at an X-ray of a number, or even, just seeing a number undressed, if you will, its bones, what it's made of. And so I'm going to do it with both of these numbers to see if I can find anything they have in common. So one thing I know is that 42 is even, so I should at least be able to pull out a 2. And if I do, 2 goes into 4 twice, and 2 goes into 2 once. Again, this is called doing a factor tree, and I have a whole long video on it. And again, I'm just going to keep dividing up each number. So 21, I know from my 3 times tables, is 3 times 7. Now, my ends of my branches now are prime, meaning I can't divide them up any further. And so I find that 42 is made of 2, 3, and 7. Now think about 77. See that repeating double digit? That's screaming at me when it's a double digit that repeats that there's an 11 in here. 11 times what? Well, 11 times 7. These, again, are both prime numbers. I can't divide them up any further. And so I'm done. And look at what I notice. They have a factor in common, 7. Now, if you have your 7 times tables memorized, you would have seen that right from the start. Do I suggest you memorize your times tables? Sure. But even if you don't have them memorized, a really quick factor tree will show you that 42 and 77 have a 7 in common. Now, looking at these numbers 6 and 11, ask yourself, if they have anything in common. You could just think about it, or you could factor tree it, and you would know 6 could break it into 2 and 3. 11's prime. I can't break it up at all. They have nothing in common except 1. I'm done. The only thing that divides both 6 and 11 is 1. I'm done. Okay. Let me erase this work. The GED knows exactly what factors you guys miss. Don't count on the GED to give you nice, easy things to see like 2s and 5s. Count on the GED to hide factors from you. And so it is important to know what to do when you don't know what to do with reducing fractions. Break that number up. Be sure these two numbers have nothing in common. Let's try it with 39 and 52. I'm going to start with 52 because there has a factor screaming at me. What I notice about 52 is that it's an even number, and I know all even numbers are divisible by 2. Now, you might not know the other side of that fact, like 2 times what equals 52, but you can figure it out through division. 2 goes into 5 twice, remainder 1, and 2 goes into 12 6 times. And so 52 divided by 2 is 26, or another way to think of it, 2 times 26 is 52. Now 2 is a prime, but 26 isn't because it's still even. You could pull out another 2. Let's do that. 2 goes into 2 perfectly once, and 2 goes into 6 perfectly 3 times. Again, I'm using short division. You should check out the video on short division if you've never done it. It is a gorgeous thing. So I see that 52 is made of 2, 2, and 13. Notice that I stopped and circled my 13. Why? Because 13 is prime. I can't break it up any further. Now, a lot of students tell me 39 is prime, and I say you're a liar. That's not true. A quick sum of digits divisibility test, adding together 3 and 9, you'll see 3 plus 9 gives you 12, which is a number on the 3 times tables. The sum of digits trick finds 3s. I found a 3. 3 goes into 3 once, and 3 goes into 9 3 times. So that means 3 times 13 is 39. So 3 is a prime, so is 13. I'm done. And do you see the prime factor these guys have in common? Look, they have a 13 in common. And you guys do not know your 13 times tables. I've met very few students who have their 13 times tables memorized, meaning you would never have found this factor unless you tried to break this number into its individual prime factors using prime factorization. Okay, we needed something. Or I shouldn't say prime factorization. This is just a factor tree. But that being said, we needed some tool to be able to look at this number a little more closely. And then when I divide 39 by 13, I have that 3 left. I took the 13 out. There's the 3 left. And when I divide 52 by 13, I take this 13 out. I still have the 2 2s left. I have 2 times 2 or 4. But you could always do the division. You could count by 13. There's a lot of ways you could see that for. So I get 3/4. Okay, let's erase this work. Do one more example just like this. Okay, 17 over 51. Now 17 might be a problem to you because there's no way to break it down. I can't even factor tree it. It's not divisible by anything but 1 and 17. But 51, a real quick sum of digits trick, 5 plus 1, will show you that there's a 3 in there. 6 is on the 3 times tables, so is 51. And so let's divide out the 3 that we see. 3 goes into 5 once, remainder 2. 3 goes into 21 7 times. And so I just found out that 51 was the same as 3 times 17. Again, another times tables you don't have memorized. You don't know your 17s. So if you don't understand a little bit about how numbers are built from prime factors, you can be in a lot of trouble and not know how to find a 17. But both of these numbers are divisible by 17. You sure could divide them both by 17. Let's do that. 17 divided by 17 is 1. And 51 divided by 17, you might be going, I don't know what that is, Kate. Yes, you do. Come look at your factor tree you did over here. When you took the 17 out, what do you have left? A factor of 3. Numbers are built out of their prime factors. It's not a coincidence that when you divide 51 by 3, you get 17. Or when you divide 51 by 17, you get 3. My writing is so messy. I'm going to rewrite that one so you guys can all see it. But I do get 1/3. So your final answers here: 6/11, 3/4, and 1/3. And I'd be willing to bet that not many of you could do this without some examination of divisibility. Just relying on your times tables might really mess you up here, especially with B and C. Okay. Awesome. If you have any questions about this or any other GED math concept, be sure to drop it in the comments. I'll do my very best to answer it.